in some of the lectures, then which is a weird experience, by the way. So I'll try to speak slower, and hopefully I'll succeed. And you can stop me if it's too much. Let's go over together the question page you had for the biochemistry of the cell chapter. So the first question. So okay, let's read the comment together. Hanchayot, the guidance together. Mark the correct answer. This is true also for the final exam. It will be the exact same phrasing, the exact same style. Only one correct answer exists. In sorting and matching questions, follow the given instructions. There's not only one correct answer that you have to sort or match as required. In what cellular function is the adenosine base involved? So remember we talked about the base adenosine, and we mentioned it in a couple of different contexts. And so which is the right answer? Let's start with A. Does the adenosine base involved in stabilizing any kind of other structures, any kind of RNA molecules, protein? What do you think? Okay, let's leave A for a minute. Let's proceed with B. Information storage. Is it involved with information storage? Where? In which molecule? So for instance, yeah, it's a nucleic acid as a nucleotide, in nucleic acid, DNA and RNA. Okay, maybe DNA is more information storage, and RNA is more information transition, but it's definitely involved in information storage. What about energy storage? What do you say? Storage and coupling, we can say, right? When it's linked to free phosphates, when it is an ATP, adenosine free phosphate, this is exactly the molecule with the highest availability of energy in the cell. About stabilizing structure, I think the answer is no, and the right answer here is B and C, which is F. If you like to. At a certain point, when we'll get closer to the exam, I'll send you the correct answers, but you can mark yourself the correct answer right now. What about question 2? Following is a list of chemical building blocks and macrostructures. Match each of the macrostructures with one or more of the building blocks from which it is built. So you have a list, and I don't say if it's a macrostructure or building block. First, you need to find which is which, and then match the two together, each pair together. Okay, who wants to try? Yes.
DNA, RNA, and nucleic acids.
Right, correct. What? And okay, anyone want to continue? Please do.
Cell membrane, phospholipid,
Exactly, cell membrane is built of phospholipid or phospholipid. I'm not sure about the pronunciation either, but okay, that's correct. And what other structures do we have? What about polysaccharides? Are built from, well, obviously monosaccharides. What about the last one? Polypeptide is built of amino acids, and that's it, right? Yeah, that's where the four structures. Right. Question 3. What type of chemical bond exists between sodium and water? So when you pour sodium, if it comes from a salt or not, never mind, but when a sodium ion charged with one plus charge, what kind of interaction does it undergo with water? What do you think? Hydrogen bond? Well, the hydrogen bond is between a hydrogen and a pair of electrons from another. You don't have a pair of electrons. Well, I'm not sure about that. Okay, so you might have a little bit of a. No, I don't think you have any hydrogen bond here. What's the most prominent or the most dominant interaction you will find in this situation? Ionic. Okay, we even gave a very similar example in class. We poured magnesium, I think, into water, and the same thing happened. It's ionic interaction. Okay, monosaccharides differ from one another in which feature, or by which feature, or maybe by none of them. So the first one, would you find different sugars in the nature with different number of carbons in them? So yes, this feature definitely differentiates between monosaccharides. you find monosaccharides having different bond conformations around their carbons. Again, that's true. See ring size, when a ring structure exists. Do you always have to have a pentose or a hexagon? Or do you sometimes have this one or the other? So you can have different ring size structures, different ring structures having different sizes, and definitely C is also a relevant feature. And the polysaccharides they form, well, different monosaccharides build different polysaccharides as a principle. So yeah, so they will be involved in different macro saccharides, different polysaccharides. And A, B, C, and D are all true. So all of the above, except the H. Okay, so all the above is true. Never mind. All of the above, all these features can be used to differentiate different monosaccharides. And I'll send the correct answers by email, maybe even today, for those of you who just came. Let's continue. So, that's true. You might have other features that are not mentioned in this question, but the question is which of the following features can be used to differentiate different monosaccharides, and the answer is all of A, B, C, and D. All of the presented features. Okay. Still doesn't work. Anyway, so we went through together the principle of hierarchical structure of proteins, and we presented the 4 structural levels, and we will now continue with different modifications that proteins can undergo after they are being synthesized. Okay, so for now we'll skip the synthetic step. Okay, let's start the discussion about the different modifications that protein can undergo in vitro. And in vitro means in the test tube or in the glass. It comes from the same Latin word as vitrage, the glass decoration. So it's easy to remember. In vitro means in the test tube or in the glass. So in vitro, hypothetically speaking, any polypeptide chain containing N amino acids or N residues can in principle fold into A to the power of N conformation. That is because there's only a certain number of angles, 8, that are chemically, spatially allowed. But still it's a huge number. And in general, empirically, you will find a certain sequence of amino acids, a given polypeptide will usually be found in a single conformation in nature. And this state we call the native state, because it is the state that is found in the nature, the natural state, we call it. And also for the vast majority of proteins, the native state is the thermodynamically most stable state. So let's plot. If we'll plot an energy, thermodynamical, I don't want to obligate to any specific kind of energy, just let's plot some energy or general energy of protein as a function of all possible configurations of this protein. Now this axis, okay, this is energy, and this is configuration. And this actually should be a multidimensional space, right? Because you have plenty of angles that can be in plenty of, you can receive plenty of values. But still, let's just compress this multidimensional space into a one-dimensional conceptual axis. So for a given protein, we'll find that this curve has some local minima, and we'll have a certain, usually just one global minimum. And for most proteins, the native state is right here in the lowest valley of the energy plot. Okay, now this is in vitro. In vivo, however, the folding of proteins is not a passive random process, but actually is being actively promoted by chaperones, and it's being actively promoted by chaperones, which are a family of proteins that fold other proteins in the cell, and we have two kinds of chaperones. Molecular chaperones, which are small molecules that bind to the polypeptide while it is being elongated on the ribosome. We will see it right in the next slide. By sticking to the polypeptide while it is being synthesized, they prevent a certain subset of possible configurations and sort of push the protein to its correct folding. The second kind is chaperonins, which are huge complexes. The protein is being inserted into the chaperonin, and inside it is being directly and very actively pushed to its right folding. Okay, so and we can distinguish between these two families by structure and by function, and the next slide will clarify this distinction more clearly. So, okay, so these are molecular chaperones, the small yellow circles. While the polypeptide is being elongated or synthesized on the ribosome, which is a huge complex that synthesizes other proteins, these small molecular chaperones bind to the polypeptide, prevent some local folding to occur, leave the protein with only a subset of possible configuration, and for some proteins this is enough to find its proper folded form and to get to its right global minimum and not be stuck in some local minima. For other proteins, the molecular chaperones only serve to guide the protein into the chaperonin, which is a huge complex of a cup shape. The protein is being inserted into the cup. We also have a cap that seals the whole complex together. And now inside, there are several known chemical reactions to occur that allow the protein, or again, leave the protein with only one trajectory in the energy curve to reach only a certain conformational state. It's properly folded form. The gray complex here is the ribosome. So while the polypeptide is exiting or being elongated on the ribosome, the molecular chaperones already stuck to some regions of the polypeptide. And then after the protein will be synthesized completely, then for a subset of the protein, the molecular chaperones will guide the polypeptide to the more actively folded complex compared to the molecular chaperones, the chaperonin. It's not in a ribosome, it's a different complex in different location of the cell. No, it's not in the ribosome.
So it's the second, the chaperonin always comes after the first?
Yes, that's absolutely. Molecular chaperones would be found, not always, but also in parallel to the synthesis, that's the right pronunciation, the synthesis of proteins. And this is not all true for the chaperonin. A protein will be entered into the chaperonin only after it is being completely synthesized.
But can they both happen together? First in the ribosome you have the molecular chaperones and then...
Yes, exactly. Together in the sense that for some proteins, molecular chaperones keep local folding, keep local folding to occur, thereby preventing aggregation, by the way, and guide the polypeptide, which is not yet properly folded, guide the polypeptide into the chaperonin, where it will be properly folded. And I think there are some models to show what exactly, in thermodynamically sense, what exactly chaperones do, and I think it's a nice and intuitive description, and I'll give it to you right now. So this time I'll plot not a one-dimensional conceptual energy or all possible conformation axis, but two, so I'll be able to plot a trajectory. So in the absence of chaperonins, when there is not just chaperonins, it's true for chaperonins and for molecular chaperones, which are together called chaperones. So there is no chaperones. When there is no chaperones, this is the plane that describes all possible configurations. Let's say that the most stable state or the native state for the protein, properly folded form, is right here, and let's call it the endpoint. And when the protein is being exited, when it is finished to be synthesized on the ribosome. Let's say that the configuration it has is right here, and we'll call it the start point. So in this energy plot, or in this energy plane, the protein needs to probe this space and to find its way from the start site from the start point to the end point. And this process has a very large random element in it, and so it might take a while. In the presence of a chaperone, never mind of which one, and again the start point and the end point, some regions of this plane are just forbidden. They are inhibited. It inhibits some of these conformations, and we are left with a much smaller subset of configuration. So now we have to probe a much smaller region to find the end site, and the process is usually much faster. So again, the principle in chaperoning any molecular chaperone is to inhibit, to make it unpassable, some subset of the conformational plane or space or wherever you want to see it. Yes?
Is there a relationship between size or the complexity of the organism and the number or complexity of the chaperones?
I have no idea. Well, I don't know. Well, and there's not, by the way, there's not such at least an obvious correlation between the size and complexity of an organism and the size and complexity of its genome. So we are very much like fungi in DNA wise. I'm not sure. I really don't know.
Are the chaperones universal, or are there different ones for specific subsets of protein?
For specific subsets of protein. Well, chaperones, molecular chaperone and chaperone is the name for a very for a group of proteins, and absolutely some, and this is why I even added this comment that molecular chaperone consists. This is very important single protein, HSP 70, Hitchcock protein 70. Never mind this detail, but okay. So this is maybe the most common example of a molecular chaperone, and it has several homologs in the human genome, which each one, exactly as you said, will facilitate the correct folding of different groups of proteins. Okay, so is that clear? Okay, we have a move? Yeah. The whole movie thing, it's not really necessary, but I think that if we have the time, then just seeing it again as a short clip sometimes can help, so here it is.
In vitro, a denatured protein. In vitro, a denatured protein can refold into its native state on its own. Nonetheless, in vivo protein folding is aided by chaperones in order to increase efficiency and prevent aggregation of misfolded proteins. Molecular chaperones, such as HSP70, assume an open form when bound to ATP. In this form, the chaperones bind nascent polypeptide chains as they're synthesized on ribosomes. The bound ATP is hydrolyzed to ADP. ADP exchange with a new ATP molecule causes the chaperones to switch to a closed conformation, releasing the target protein. A second class of chaperones, the chaperonins, is required to help a small proportion of proteins fold properly. A partially folded or misfolded protein is inserted into the cavity of the chaperonin, where it can fold into its native conformation. ATP binding causes the chaperonin to expand and release the protein properly folded.
Well, here the chaperonin is really a magic box that you put inside an unproperly folded protein, and in fact, there are nice models to show what exactly happens. They try to show it, what exactly happens inside chaperonin. It's not in the scope of this course, but you're very welcome to check it out. It's Google. Okay, so after a protein is properly folded, it undergoes several additional modifications. And the most common one, sorry, so before, let's just say that a modification, by modification we mean usually a linkage of some chemical group to some region of the protein, and it can be either to its C terminal, which we defined last time, or to its N terminal, like the C or the N terminal of the protein, or to an internal residue, meaning some amino acid in the body of the protein. And such modifications can affect several aspects in the life of a protein. For instance, it can lengthen or shorten the lifespan of a protein, change the cellular location where the protein is, and alter its activity, and so on. And the most common modification that's found in the cell is called acetylation. Acetylation is an addition of an acetyl group, which is this chemical group, to the amino group of the N-terminal residue. Again, we're talking about the N-terminal of the protein. This is the N-terminal, and this is how an acetylated N-terminal looks like. We just added an acetyl group to the N-terminal of the polypeptide. And it's a very common modification because non-acetylated proteins in the cell would be very rapidly degraded by other proteins that are called proteases. The suffix ases means proteins that perform cleavage, usually afterwards degradation, but cleavage on the protein, on the molecules that are before the suffix. So proteases are proteins that cleave proteins. Cleavage, cutting of the polypeptide chain. Okay, so as I said, acetylation is perhaps the most common chemical modifications on proteins in the cell. Let's see some additional modifications. So for instance, glycosylation. Glycosylation is the linkage of a saccharide somewhere around the protein. It's a very common modification for a secreted protein, proteins that are synthesized in the cell and secreted to the cell environment, because it has a protective property that protects proteins from the harsh environments that exist outside of living cells. Acetylation can be also not only on the N-terminal, but also on some internal residue, for instance, lysine. In this case, it will no longer be called a simple lysine, but it will be called an acetylysine. Phosphorylation is the addition. Once again, phosphorylation is the linkage of a phosphate group to some other amino acid, for instance, serine. In this case, it will be called phosphoserine. It's usually a transient modification. So coupled to phosphorylation, we will find dephosphorylation. And you have several other examples that we won't go into. And just to note, so how many amino acids do we have in the cell, remember?
20.
We have 20 amino acids, but when taking all possible modifications into account, you actually effectively have more than 20, right? Instead of serine, you can have phosphoserine, acetylserine, or hydroxyserine. And each one will have, well, different function in protein. So again, effectively, we should always remember that we have more than 20 amino acids, simply because of the modifications they can undergo. Okay. The principle is what's important from this side, right? Not the details, which is what I try to convey from the question pages. So for instance, the principle here is that there are several different modifications with several different functions, and each can occur in the N or the C terminal or in some internal residue. This will change the properties of the amino acids that have undergone the modification.
What is the acetylation in the group to the N-terminal?
It's not, the amino group here belongs to the lysine amino acid. This is the N-terminal of the amino acid. And so this is not an N-terminal acetylation, as was the case before, when it was just linked to the exposed N-terminal of the polypeptide. It has an end, right? So the N-terminal of the protein is most usually acetylated in protein. This is in the body of the protein. This amino acid. Yes? You want to ask something? Okay. of chemical groups can happen on to proteins, but also processing out, meaning removal of some fragments of protein. And this process is usually effective when we talk about mechanisms in the body that need to react very rapidly to some input. So, for instance, in blood coagulation, you sometimes find processing of proteins in the sense that some fragments of them are removed. So, for instance, when we are injured and start to bleed, some proteins or some fragments from some proteins are removed, and this causes these proteins to gain some function. In this specific case, to aggregate to one another and coagulate, and the bleeding stops. Now, and the idea again is that you don't have to synthesize a new protein. You don't have to synthesize a new RNA even. You have a protein already in the cell, but it's not active yet. And given a certain input, the insult, the injury, so this mechanism will be activated, and the protein will start to coagulate. You have a very rapid response, the most rapid response that the cell can give you using this mechanism of processing of certain fragments of protein out of the protein. Okay, I think a nice analogy is like a knife with a sheath, סכין בתוך נדן. So you already have the knife and the sheath inside the cell, and all you have to do is to take out the sheath or to cut it out, and or to take out the cover for the knife to become functional, right? So it's a very rapid response. That's what this process gives you. Yes.
The knife is in the cell or in the protein?
So the knife is the protein that's in the cell.
So
Very
it's a
quiet.
different protein?
Sorry?
It's a different one?
No, the analogy means that if the protein that can undergo processing is sort of like a knife that's not functional as long as it's in its cover, when you take it out, it can do what knife do. Yeah, maybe it's an analogy, but the knife here is sort of the protein that undergo processing. The removal of some fragments of the protein is the removal of the cover of the sheet. Okay. The activity of proteins depends on their level, or how many proteins you have in the cell, and this in turn depends on the balance between the rate of synthesis, how much protein do you synthesize, do you produce, and the rate of degradation, which is a very actively regulated process. Okay, different proteins in the cell have a large variety of life lengths. For instance, proteins that play a part in cell cycle, where you have to have a very precise, time-wise, a very precise regulation, live just several minutes, can live several minutes, meaning that you will have just a couple of minutes from the second that they are produced to the second they are already very actively and rapidly degraded. And maybe the other edge of the scale is proteins that reside in the lens of the eye, which are just as lived for several years as the lifespan of the organism itself. So after they are produced, they are just stay there until we die, and they have no degradation at all, no active degradation. Degradation is different for extracellular proteins that are secreted to the cell environment, and to intracellular proteins. Extracellular proteins undergo degradation inside lysosomes. We will see the structure precisely, exactly how it looks and so on in a chapter after the next. But for now, lysosomes are just vesicles that bud out of the cell membrane into the cell, and they take with them a fraction of the environment, a fraction of extracellular proteins. And inside, the pH is very acidic, and they have some specific proteases to break down and degrade these proteins.
So the extracellular protein from the outside,
Yep.
and inside is degraded?
Degraded, exactly. Degraded. On the other hand, cytosolic degradation, meaning proteins that are inside the cell, usually would be marked with a ubiquitin, which is a 76 residue polypeptide. It's actually an additional modification, pretty large one, but just a chemical modification that tag the proteins for degradation. And the proteins that are sufficiently tagged or marked with ubiquitin will find themselves in the spliceosome, which is a sort of a slaughter machine that breaks down proteins back to their building blocks. Okay, this process, ubiquitination, and its particulars were revealed and characterized by two Israeli scientists, Hershko and Shachanover, who won the Nobel Prize for it. So let's go over very briefly at least some of the particulars of this process. Let's start with the third step. In the third step, this is where the interesting thing happens,
Talking about
ubiquitination.
inside the cell.
Which is the process that regulates degradation of intracellular cytosolic proteins.
What is ubiquitin?
Ubiquitin is a molecule. What it means? Ubiquitin is something that can be found that is very very frequent in the cell. I think that's what the meaning of the word. That's what the word means. Something that is very ubiquitous is something that you can find everywhere. And this molecule is found in lots of places in the cell, and thereby it's ubiquitous, and thereby they call it ubiquitin. In this step, this is when the ubiquitin right here is really attached to the target protein. Yeah, this is the target polypeptide or target protein that would, at the end, will find its death in the proteasome, sorry, not the spliceosome, in the proteasome. But before that, it has to be tagged several times with ubiquitin. So the first step is where the ubiquitin is being attached to the protein. But you have to have two preliminary obligatory steps. In the first one, protein is called ubiquitin activating enzyme would attach the ubiquitin to its colleague ubiquitin conjugating enzyme, and only this one would be able to mark the third party in this agreement, the target protein itself. You don't have to remember the details I've just mentioned. And after the protein is after this process repeats several times, and the target protein is tagged with several molecules of ubiquitin, it is sufficiently marked, then it is recognized by the cell to be guided into the proteasome, where it is chopped back to its building blocks.
And before the ubiquitin, you have one enzyme that has to be attached to it, and you said
Certain enzymes sort of prepare the ubiquitin molecule
okay.
to be attached on the target protein. Just remember this part simplified as I just said, and then the ubiquitin is attached to the target protein.
And then it has to repeat itself.
Yes, and again you have to have another linkage of another ubiquitin on the first one, and a third one on the second one, and so on, until it's sufficiently ubiquitinated.
But the ubiquitin itself does not degrade the...
No, it's just a flag, it's just a mark, it's a tag on the protein. It has no proteases properties. Let's keep the movie for now, because I like to go on with enzymes. Okay, so we will now introduce two families of proteins that perform specific tasks, and meaning enzymes and molecular models, and we will describe exactly how their how their structure give rise to their function. So enzymes are a specific family of proteins that promote chemical reactions. A protein can bind a molecule and not necessarily change its chemicals. So if a protein, globally, when a protein binds a molecule, we will call the protein a protein, and the molecule that is binded to it a ligand. And when the protein changes chemically its ligand, then the protein is called an enzyme, and the ligand is called a substrate. So the substrate is a maybe specific case of ligand. Okay, what exactly enzymes do, thermodynamically speaking? So we've previously plotted the energy curve for an exothermic reaction as monotonically decreasing. I will plot it again right now. So if these are the reactants and these are the products, we plot the energy curve as monotonically decreasing from the left side to the right side, but most usually this is not the case, and there is an increase before the decrease begins. And you have to pass a certain threshold before this reaction can really happen. And this threshold is what we call the activation energy. Almost all reactions in the cell have such a threshold, and hence have some activation energy different from zero. And what enzymes does do in this sense is decreasing the activation energy, which allows the reaction to take place much more efficiently. So actually, chemical reactions will happen in the cell even in the absence of enzymes, but with very slight changes. And enzymes can promote this chemical reaction 1,000-fold. This is why we say that enzymes have immense catalytic power. That in their absence, compared to when they are in the system, the chemical reaction will be promoted in really sometimes tens of thousand-fold. Also, every slight change in the enzyme's substrate, and it will no longer be recognized as a substrate. So, enzymes have a high degree of specificity to their substrate. Certain amino acids in the enzyme form the active site. And more specifically, the active site consists of two sub-regions. The first one is the one that are the amino acids that bind the substrate. This is called the one that binds the substrate, which is the binding site, obviously, sorry. And the other that really catalyzes the chemical reaction, which is called the catalytic site. The binding site together with the catalytic site is the definition of the active site of an enzyme. Okay, now let's see a specific example of an enzyme, and I think that besides the particulars I will explain in a minute, it will also convey the principal function of enzymes. So this is pKa, protein kinase A. It has a large domain. It has a region we call the small domain. It has a region that we call the glycine lead. It's like a cover that undergo a substrate-induced fit. Remember that last time we said that the tertiary and quaternary structure levels of the protein undergo continuous fluctuations, sort of breathe. They have some slight movements continuously, and when the substrates of pKa are recognized by it, the glycine lead lock these two substrates together, and no longer such fluctuation is possible around this area. So the glycine lead locks the two substrates together, and this is exactly what we call substrate-induced fit.
You have here two substrates?
Well, maybe ATP shouldn't really be termed as a substrate here. The substrate of pKa is actually the target protein that we're about to add a phosphate group to it. So before that, the task that pKa performs is addition of a phosphate group in specific protein, in specific fragments of other proteins. So the substrate, the real substrate of pKa is the target peptide, here in red, which pKa binds because of the interaction with this target peptide and the amino acid of pKa underneath this peptide. We have other protein kinases, protein kinase C and so on, and these will be different between them in the amino acids right here beneath the target protein, the target peptide, and this will cause each protein kinase to recognize different sets of target peptides. Okay, so different protein kinases differ between them mostly in this region where they bind to the target peptide. And another site that pKa has is an ATP binding site, and we need ATP because we're about to take phosphate from it and transfer it and link it to the target peptide, thereby perform phosphorylation on this peptide. in every protein kinase. Well, not in every enzyme. Some enzymes, will maybe show less of this picture. But here it's very obvious. You have this glycine lead that really locks or lowers and locks the two substrates together in the active site, which is right here, and which is where we are going to zoom in right now.
You didn't
Yeah,
talk about the substrate induced and the other kind of.
Okay, so again, so I'll clarify it again. So substrate induced fit is a specific case of tertiary of the feature that we mentioned in the tertiary structure context, that the tertiary structure undergoes continuous fluctuations. It's not a rigid structure in opposed to the secondary structure, for instance, alpha helices and beta sheets, which are rigid. So this one continuously fluctuates, and upon some induction, for instance, recognition of its substrate, it can be locked and be rigid again. Okay.
Just I remember with the cellular code,
Yeah.
there is two kinds of substrate splitting, which is one is substrate induced and one is
Allosteric?
Huh?
Allosteric?
No.
I'm not really.
Something with the substrate split the enzyme naturally with not induction.
Okay. So we're not, we'll not use this terminology here. We don't need it here. But let me find out with you afterwards exactly what exactly are we talking about. But we will just not use this terminology here. So now let's zoom into the active site of PKA and see exactly what happened inside it. First, let me describe exactly what we see here. So in black is the ATP, adenosine 2-phosphates, and in what is purple? In purple is the last phosphate in this chain that's about to be transferred to the polypeptide, to the target polypeptide, here in blue. Everything else is the amino acids in the active site of PKA, and we also have some ions that interact with these amino acids. Okay, so these are the flavors. These two positive charges interact with the phosphate groups and delocalize the electron clouds around this phosphate group. And this delocalization is what making the link that's about to be formed possible. And this again, this electron delocalization is what's shaken the bond that's about to be breaking right here. And this is exactly what we call the intermediate state. It's a very transient state. From here, we can slide back to the initial state, or slide down to the reactant side, to the end state. This intermediate state is highly unstable, at least in relation to the initial or the end state, and it's exactly the state that's being stabilized by the PKA. The threshold you have to pass, the energy of this species is exactly the activation energy, and exactly the energy that the PKA lowers by stabilizing this structure. And stabilization, again, is by the positive charges here, and to them we know that by additional moieties that are in the active site of PKA, but let's focus with these two positive charges that delocalize the electron clouds.
So this is the state with the higher energy?
Yeah, this species right here in the energy curve. This is exactly the threshold, yes?
But is PKA in the picture?
PKA, we are looking, the next slide is zooming in on this active site. Here you see the ATP in green and the target peptide in red. This is the active site we are going to zoom in right now. We're in the stomach of PKA. Okay.
Can you repeat what happened with the, you said that there are two positive sites and then
Two positive charges by the magnesium that are held in specific distances from this phosphate by amino acids from the active site of PKA. Right? So these magnesiums are here not because they want to, because they are enforced to by the active site of pKa, and they cause some electron delocalization around the last phosphate of the ATP. Okay, so again, we can slide back to the initial state, but if we do so, we will meet the glycine lead that locks these two substrates together. And again, we will be pushed towards the intermediate state. And if we slide down to the reactant site, where this is actually the product of the reaction, here you see the red polypeptide with the linked phosphate. This peptide is now phosphorylated. The pKa succeeded in its task, and we are left with an adenosine diphosphate, ADP. So in this case, the glycine lead opens, and these two products dissociate from the active site. So you see that it's a very essential role of the glycine lead. So because each time you kind of slide back into the reactant site, the glycine lead reminds you that you have to, or pushes you towards the end state, where it will be open, and this product will dissociate from the active site. And this what gives pKa its enormous catalytic power of this reaction, adding phosphate on the target peptide. Questions about this mechanism? Okay, last slide for the break. We just comment about the fact that cells have evolved and coupled some chemical reactions in which the products of one reaction have to be introduced as reactants to a second reaction when two reactions are coupled. And cells have developed very effective mechanisms to couple spatially these two coupled reactions together, simply by assembly of the enzymes that promote each of these reactions, assembly of these enzymes on a common scaffold. So this is a specific example of such clusterization of enzymes as subunit of a multimeric enzyme. For instance, pyruvate dehydrogenase is a multimeric enzyme. It's multimeric because it's built from enzyme 1, enzyme 2, and so on. The net reaction that pyruvate dehydrogenase does is hit down here. So for instance, pyruvate comes from here and will find itself at the end as a part of the acetyl-CoA, here in purple, here in purple. You have to have some energy to drive this reaction. It comes from here. You have to have CHO exiting that system, and so on. So again, each of these reactions, was located in different compartments in the cell, it will be much less effective than if the three enzymes that play a part in these coupled reactions are assembled together on a common scaffold, which in this case, the reactants of, for instance, E1 immediately being introduced as the products of E1 immediately being introduced as the reactants to E2, and so on.
Can you define what is common scaffold?
Common scaffold, just, for instance, you will have some, structurally speaking, so you have some additional proteins here that are not plotted that simply glue or stick these three enzymes together spatially. Hold them into correct configuration to make this coupling not only chemically speaking, also spatially speaking. So this principle is that it promotes the effectiveness of enzymes. Let's take a break, and afterwards continue with molecular motors. Let's take 10 minutes break. אז לא הייתי אני אוסיף אותך ואני אשלח לך את אלה שכבר נשלחו, את המיילים שאפשר.
But I think it's rather useful because we can compare when I think it's confusing more. That's why I want to meet with them.
Yeah. זה, אם אתה לא זורק עליי דברים, אז אתה תקבל את זה. לא, אז זה באמת כזה בשביל מי שמהכרה, כאילו זה מנגנון שזה פשוט...
אפשר לשאול קצת על השקף האחרון?
כן, בהחלט.
האזורים כאילו השונים, הם כאילו יושבים על אותו חלבון, או שיש כאן חלבונים שנקשרים מרחבים?
טוב, אני לא יודע, זה טרמינולוגיה, כי למשל אני לא הגדרתי גן, בואו נראה, E1 זה חלבון, אנזים 1, אנזים 2, אנזים 3.
אוקיי.
יש להם גם פונקציות בנפרד לכל אחד,
כן.
אבל כשהם מחוברים ככה ביחד, הנט ריאקשן הזה, כאילו, כן, האפקטיביות שלה עולה עשרות מונים.
אבל אתה מסתכל על E1, E2 ו-E3 כשלושה חלבונים, או כחלבון אחד גדול?
כשלושה חלבונים, ואז אנחנו קוראים למולטי... זה לא קריטי. יש בזה המון טרמינולוגיה, וכל חוקר ישתמש בטרמינולוגיה שבא לו. I don't find it so essential.
Okay.
To go into the precise terminology, it's not that important. פה, זה מתוך הספר, הוא קרא לזה מולטי אמריקן, לא אם קראתי לזה גם. אפשר לקרוא לזה גל, ממש. חלבון אחד, או שאפשר לקרוא לזה... זה מאוד פאזי. כל אחד אני שומע קורא איך שהוא רוצה.
אוקיי. תודה.
Myosin
נראה לי ממה שמעתי על הנושא הזה, שתוחלת חיי עד לרגע האחרון.
תזכירו את השמות רגע, נעשה את זה בבוקר.
אדר.
אדר.
נמרוד.
נמרוד. אורן. נוגה. Remind me your name. Kate, right? Okay, Benjamin.
לא.
Sorry.
יונתן.
יוני, sorry, נכון. יונתן, נכון, אמריקה. ואיך השם? אני לא יודע. גבי? Okay. Proteins do so many tasks in the cell, and among them molecular movement or cellular motility. It is done by a protein family that's called protein molecular motors. Right.
Is your microphone turned on? Because it's something.
It's only automatic.
Okay.
No, you don't need to hear me here. It's how passes through the system, and I'm not sure. They told me not to touch anything. I'm not touching anything. Don't touch anything. Okay. The principle by which molecular motor actually couples chemical energy to mechanical energy, to movement, is by a series of conformational changes in the motor protein, which couple ATP hydrolysis to movement. And the central players in cellular motility are the myozymes.
Hydrolysis of ATP becomes ADP.
Yeah, hydrolysis of ATP means that you hydrolyze or dissociate breaks one phosphate from the ATP to become ADP, which gives you the energy for the cellular movement. Okay, and we will describe the molecular motors called myozymes, which again is a family of proteins. Several myozymes in several tissues, in different tissues, and but principally they all have a head domain, right here in the schematic representation or in the ribbon model, the head domain and neck domain. What's protrude from the neck is the tail domain, and each one has a specific distinct function. On the head domain of myozymes, you'll find the nucleotide binding site. This is where the ATP that gives you the chemical energy binds to. And it also has a binding site to actin, which is the protein against which the movement will take place. It's like the road. Okay, you have to have some contra on which to perform the movement, and this scaffold is exactly actin, which will bind right here in the head to the head domain of the myozyme.
Can you repeat what's the function? The actin binding site?
So the actin is another protein that serves as the road on which the myozyme head will move, against which the myozyme head will move. This is like the wheel of the car, if you wish, and this will be the road on which the movement occurs. Okay, let's see the cycle and mechanism exactly, and perhaps it will be more clarified afterwards. So we now introduce, I'll just bring the old slide on, because I don't have the, and then we will go step by step. Okay, this is the cycle of cellular motility. The principles that are shown here are true also for movement of organelles inside the cell. So for instance, if we talk about neurons or vesicle filled with neurotransmitters that is produced in the soma, in the body of the neuron, which has to get to the edge of the dendrite, for instance, to the synapse, will be moved along the this is the mechanism for muscle contraction and other cellular motilities or cellular movements. So the myosin head is linked to a thick filament, and it would perform a step in relation to the actin thin filament. So this is the road, the wheel, and the car, if you wish. And these two filaments, the thick blue here and the thin actin filament, these red circles here, are going to be moved in parallel to one another. This is our task for today.
Where is the protein that you want to move, or where do you want to move?
Instead of a thick filament, think of an organelle filled with neurotransmitter, of a transporter that is produced in the cell body and needs to get to the synapse. Instead of the thick filament, is exactly where the protein you want to move inside the cell is linked to. Instead of the thick filament, okay? So just imagine that the myosin head is linked to the thick filament to another protein that you need to move somewhere into a new location in the cell.
So what is this thick filament?
So this is the description for muscle contraction, and the thin and thick filament are sub-tissues inside muscle tissue. They are just alignment of proteins aligned together that form specific, I don't know if I can call it sub-tissue, but specific filaments along the muscle tissue. So the description here is for muscle, but it holds true also for inside cellular motility. Okay, so the first step begins when there is no ATP in the NTP binding site. And in this case, the myosin head binds tightly to the actin filament. And actually, this situation where in the absence of ATP, you have a tight binding to the actin thin filament, it's the basis of what is called a phenomenon that is called rigor mortis, stiffness of death. So if you ever try to take a ring of a dead man's finger, you probably notice that it's very hard because the muscles are contracted. And the reason is that after death, when the pull of ATP is done, then all myosin heads just stick to the thin filament in front of them, and which perform an array of very tight interactions, which is very hard to break. So maybe a single interaction between a myosin head and a thin filament, you'll be able to break right away, but a couple of millions is a different story. Okay, so back to the livings. If we have ATP in the system, so when the ATP will be introduced into the ATP binding site, we will have our first conformational change in the myosin head. It releases its binding with the thin filament and kind of contracts a little bit backwards and stays this way. Upon hydrolysis of the ATP right here, so the ATP is a red rectangle here. Upon hydrolysis to ADP and a separated long phosphate, the myosin head moves to a new location on the thin filament, binds on a new location on the thin filament. And up till now we had no movement between the two filaments, right? Just a series of conformational changes in the myosin head. But what good is it for us? We still didn't move the thin filament compared to the thick one. So are you ready for the movement? Upon dissociation of the long phosphate from the active site of the myosin head, we get what is called a power stroke, where the myosin head contracts with great strength backwards, and upon dissociation of the ADP from the ATP binding site, we are coming back to the first step of the tight binding with the new location on the thin filament with no ATP in the binding site.
So it looks like what's moving here is the thin filament, not the thick.
It's one compared to the other. It depends on where do you hold, to where the muscle is attached, right? To which bone, which side of it. The main thing is that you have a movement in one compared to the other. So again, these are the particulars. Now the principle. You see here a coupling between a series of chemical modifications, right, on the ATP, hydrolysis, dissociation of the wrong phosphate, reattaching, and so on, with movement of the myosin heads. Movement meaning conformational change of the myosin head. This is exactly a good example of energy coupling. Okay, now let's go over again the sequence of events by seeing a movie of this mechanism exactly. And here it is.
Myosin motility is coupled to ATP hydrolysis. The following mechanism pertains to myosin 2, but all myosins are thought to move the same way. ATP binding opens the cleft, disrupting the actin binding site. This causes myosin to release the actin filament. With ATP hydrolysis, a conformational change rotates the myosin neck and partially closes the cleft, restoring the actin binding site. Myosin rebinding to actin catalyzes phosphate release and activation of the power stroke. The final step of the cycle is ADP release. Movement of myosin along the actin filament continues as the cycle is repeated. In this case, the myosin molecule is tethered, so the resulting action is sliding of the actin filament.
The plus and minus here at the two edges of the actin filament denote that it has a direction. It has polarity, and so the myosin head will move towards one side and not towards the other. As is the case of unidirectional strips, which have less accidents. So instead of two micelles go and bump into each other and make a car accident or a missile accident, the actin filaments are unidirectional and have, due to their polarity,
So it always moves to the plus side?
towards the plus side. I think there are some myosins that move towards the other side, towards the minus pole. I'm not sure, and I'm not sure. The thing to remember here is that the road itself has polarity and has directionality. Okay, now. The next point is about common mechanisms for regulating protein function. And actually, we have discussed several mechanisms of protein regulation. For instance, the modifications are regulating protein function, and also the processing out of fragments. But now let's just maybe just very briefly describe some additional concepts in this regard, and do it maybe in a more ordered fashion. So let's begin by saying that the catalytic activity of enzymes or other proteins is regulated to meet the needs of the cell. This is like the job of the regulation mechanisms to adjust between the needs of the cell and the amount or the activity of the enzyme or other proteins. And allosteric mechanism is a mechanism in which a protein changes its tertiary structure upon binding to of a molecule to anywhere on this protein other than the active site. So, for instance, in the case of enzymes, if you would bind such another molecule that will compete with the substrate of the enzyme on the active site, then obviously it will change the activity of the protein. But when we talk about allosteric mechanisms, we exclude this case, and we talk about a situation where some molecule, and we should call it a ligand because it binds to a protein or to an enzyme, some molecule binds to a protein somewhere outside the active site, thereby changing the affinity of the natural ligand to the binding site of the protein. Okay, so thereby changing, if it increases the protein's activity, we should call this molecule activator, and if it decreases the activity of this protein, we should call it inhibitor. The came again, and the last time, allosteric mechanisms in the linkage is the binding of a molecule to anywhere on the protein outside the active site, which changes structural of the protein and changes the function of the protein correspondingly.
This protein is enzyme?
It can be an enzyme, or it can be another protein that does not change chemically its ligand, and thereby shouldn't be termed an enzyme. And we'll see some examples in the next slide. Yes.
Is the conformation change of the chaperones also considered as allosteric?
Yeah.
With the ADP and ATP change?
ATP is usually not referred to as a ligand that changes, but the change in tertiary structure of a protein by allosteric mechanism. Even though it does so, simply because I think the mechanism, I'm not sure, I'm not sure. But usually it's not ATP, which is maybe a unique case of energy coupling. Here you don't really have such a case. No bond needs to be broken even. You just have to have some binding of the molecule outside the active site on a protein, which changes the protein's functional structure and hence its function. Let's see some specific examples, and maybe it will be more clear.
When you talk about an active site, it's always an enzyme?
Okay, so in an enzyme, the active site is where you the two regions together, the binding site and the catalytic site. But the active site on a different protein that is not an enzyme is just a place where its ligand binds to it, and by ligand and not some other molecule that perform a tertiary that perform allosteric mechanism. By ligand I mean the molecule that the protein binds to and convey its main role. Let's see some examples, and I think it will be more clear afterwards. And if not, so please do ask me again. So, some examples for allosteric mechanisms. So, the first one we will discuss is what we call cooperative binding. This is colmodulin. Okay, I'm trying to answer your answer in parallel to the explanation of cooperativity. This is colmodulin. It's a protein that, upon binding to several calcium ions here in green, would change its conformation and would thereby bind other target peptides. So in this case, the terminology should be that the target peptide is the ligand of the colmodulin. And these molecules are maybe co-ligands, you can say, some people call them co-ligands, where they also bind, because they also bind to the protein, but are not the main, no specific task is performed on them, but on the target peptide, right? So this is the main ligand, and this is the, maybe a co-ligand that changes the tertiary structure of the protein, and only then this protein gains some function, for instance, binding of other proteins, some fragments of other proteins. And in colmodulin, we see the phenomenon that's called cooperative binding, which is, first in cooperativity, you have to have several binding sites, because cooperativity is exactly the interaction between several binding sites. So cooperativity is when the binding of the first calcium ion would change the affinity of the protein to the binding of the second calcium ion, and the second binding would change the affinity of the third binding, and so on. So you see that you have to have more than one binding site in a protein to talk about cooperativity. If the binding of the first calcium decreases the affinity to the second ion, we call it negative cooperativity. If the binding of the first ion increases the affinity to the second ion, we call it positive cooperativity. And if the binding of the first ion do not change at all the affinity to the second binding, how should we call this cooperativity? Neutral, or just, we don't have cooperativity. Each binding stands to itself and is not dependent on previous binding. So this is cooperative binding, which we see in colmodulin and other proteins. Some ligand binding can induce allosteric release of catalytic subunits, which, as we said, release of catalytic subunits meaning that some fragments of the proteins are removed, and which expose some other regions in the protein and give this protein some gain of function. And more specific examples of molecules are calcium, which we met right here, GTP, which is guanosine 3-phosphate, and phosphorylation, which are widely used in the cell to modulate protein's activity by allosteric mechanism. And these two schemes are just to convey the idea that, for instance, GTP and phosphorylation by allosteric mechanism can switch protein from an active on state to an unactive off state. So again, for instance, the GTP here or the phosphorylation here will occur outside the active site of protein or outside the active site of an enzyme, would change the tertiary structure of the protein and thereby change its function as well. So these were just a few additional words about common mechanisms of regulating protein function. And we will end this big chapter with describing some of the methods we have in our lab, we have in any lab, to purify, detect, and characterize proteins. So an obligatory preliminary step would be to purify a protein if you want to investigate its structure and its mechanism of action. And so many methods are involved in laboratories to purify proteins. You can purify proteins by using each of their characteristics, their charge, their size, sometimes their shape, their affinity for binding other molecules. And according to Lodish, anyhow, the two most widely used characteristics are by binding affinity to specific ligand or by mass of a protein. These 2 points will be clarified in the next slide, but again, you can purify proteins using each of their characteristics. So, for instance, if you have a small protein and a large protein, I will describe in a minute methods that you will have to purify, to separate the one from the other. Purifying, separating. So usually we begin, for instance, if you want to check a protein or isolate a protein from a mouse brain, you will take the mouse brain and homogenize it, just chop it, make it into a soup. And from the soup you would want to take out, or the final step that you want to get to is to have a specific protein in a specific test tube. So you wish to fractionate the homogenate, or the soup, meaning that you wish to have a specific, or at least to enrich, right, a specific test tube with a specific protein. And the following methods do exactly this task.
You find this just differentiating between proteins?
Again, purifying this, separating between proteins, yeah, in this context. It's exactly the same.
According to their metal length or size.
Right, exactly. So we will usually start by, so this is exactly the brain homogenate, and we will usually start by removing by using a very rough separation of just a regular centrifugation, removing large molecules that we don't want from our soup. So if you centrifuge it according to a specific protocol that was tried, in the past empirically, you will find this centrifugation will form a sediment, mishka, and a supernatant, tarchif. In the sediment, most usually you will find cell membranes and cell organelles that have not been broken during this process. And in the soup, or in the supernatant, you would find nucleic acids and also proteins. And you can easily separate between the two. The supernatant is stuck to the bottom of the test tube. Sorry, the sediment is stuck to the bottom of the test tube. You can just pour out the supernatant to a different vessel and continue to do a more refined separation, again by centrifugation. This time, not inside an empty test tube, but inside a test tube that has inside it a sucrose gradient that becomes thicker and thicker as you go down this test tube. So this is a more dense matrix than more towards the opening of the test tube. And you'll centrifuge it in so and so G-force and so several minutes. No, it's a bit maybe counterintuitive in the sense the larger the protein, the bigger the force that it will oppose the sucrose gradient, and the more towards the bottom you'll find this protein. So larger proteins are found in the bottom of the sucrose gradient, in opposed to small proteins that are found more towards the opening. It's counterintuitive because maybe smaller proteins can get more far, and in some methods this is exactly what happens. But here, it depends on the force that each protein opposes the sucrose gradient. Yes.
Is the two-protein solution?
It's a solution. It's on something. It's like a gel, something between a solution and a salt. There's a term for this state. Something like a gel.
So it doesn't, like, the gradient doesn't go away over the time?
The sucrose.
Yeah.
Well, maybe if the centrifuge is too long, I guess it does affect the gradient itself, but not. But for the right protocol, it shouldn't be affected.
Continue to separate the archive.
Yeah, the supernated archive.
And what is inside the archive?
Well, other than proteins, you will find there nucleic acids, DNA and RNA. Maybe even fractions of cellular membranes that are very, very small, and were not able to be sedimented at the bottom of the test tube. Okay, this is a very rough separation, and even more fine separation is by a method called electrophoresis. We will not see the movie. Okay, we begin this method by coating the proteins with a detergent. Usually it's SDS, which is sodium dodecylsulfate. That's what SDS stands for. And we coat the proteins, and SDS coated proteins have a negative charge. So now when you put them inside an electrical field, they will start to migrate towards the positive pole, towards the cathode. And in this case, the smaller the protein, the more towards the positive pole you will find it at the end, because the gel on which you let the proteins migrate is a cross-linked polyacrylamide gel, is a very dense mesh of a specific protein. I think the protein it's a very dense mesh of this molecule, and the SDS treatment denatured the proteins, meaning that it destroyed any tertiary and secondary structures. And now each protein is in the form of its only is only left with its sequence of amino acid, its primary structure. Each protein is now just a snake that snaked through the polyacrylamide gel. And so the smaller the protein, the farther toward the more towards the positive pole you will find them, because they will be more able to snake through the dense mesh of the polyacrylamide gel. And the bigger proteins will stay behind to more towards the negative pole. And you will get bands of proteins of different sizes. Okay.
In this method, you represent the proteins according to their size or mass.
Or length. Right. The most precise description of electrophoresis would be separation by charge to mass ratio. And let's not go into that. It's like a nuance, and it's not that important. The length of the protein is the most dominant aspect that is by which the proteins are separated in electrophoresis. The length of the protein. Okay, this is a cool variation or development on the classic electrophoresis, which is where you separate proteins using two characteristics at the same time. We start by separating proteins by what is called the isoelectric point, by doing isoelectric focusing. And the thing is that in different pH, each protein or each amino acid on each protein gains some charges, and in another pH, the same amino acid loses its charge. And for each protein, you find a specific pH in which the number equalized to the number of negative charge, and the protein is hence neutral and has no net charge. And if you put this protein now inside an electrical field, it will feel no force, right? You have only force in electrical field when a substance is charged. So if you put a protein, if you load the proteins right here, they will start to migrate, and you will introduce an electrical field to this system. Proteins will start to migrate because they will have a charge and hence will feel an electrical force until they will get to a certain pH on this pH gradient in which the number of negative charge equalizes to the positive charge. They have a net charge of 0, and they will stop moving because they will feel no force anymore. This point is called the isoelectric point. The pH where the net electrical charge of the protein is 0. Okay, this was the first operation, but by the isoelectric point. Then you just take this scale, flip it to 90 degrees, and separate it using a classical electrophoresis separation by size, and you get this nice blot in which, in this direction, proteins are isolated or separated by the isoelectric point, and in this axis they're separated by the molecular weight. All in all, you see, or there are some smears here, never mind why, but we do see here that proteins are separated less or more equally in both axes. So each dot here is a protein or a very similar protein family, very similar and small protein family, but principally each dot here on this blot is a protein. And for instance, if we would only use the isoelectric focusing, so the proteins having the same molecular weight would not be separated, and vice versa if we will only use the molecular weight separation by electrophoresis, and only when we use the two of them together do we get separation between some of the dots here. And now we can see, for instance, if in the biological case A, do we see a different, less darkened, less intensity of the staining of these dots compared to a biological case A, or healthy or disease, cell type A, cell type B. In this way, these blots can be used to separate and even semi-quantify proteins.
So
Two
if there
digits.
is a third aspect that separates the intensity of the...
Well, it's not, no, so the intensity of each dot here, let's say like this. If you have this dot here in a healthy individual and it's absent from the blot in an individual with Alzheimer's disease, so we would say that the Alzheimer's disease do not have this protein, and how do all you have to do now is to identify this protein. But you've identified a dot on your blot which is missing in a disease, for example. And you would not see it if you would only separate proteins using one of these features, right? You have to use both of them together. So 2DGL is the way to do it. Okay, liquid chromatography is a general term for a family of methods in which we pass a mixture of proteins inside a column, and the molecules interact with the matrix or the surface of what's inside of the column. And the principle is that molecules or proteins that interact more frequently with whatever we have inside the column are delayed and will exit last, in the last fraction from the column. And now we'll see some examples, specific examples for liquid chromatography. So the first to be discussed is gel filtration chromatography, which separates proteins by their size. In this case, what you have inside the column are beads with small depressions scattered around them. Small proteins will interact and fall into these depressions upon these beads. Thereby they will be delayed and will exit last. So again, it's a bit counterintuitive because the small proteins exit last. It's maybe because I would say that big proteins stick longer inside the column, but in this case they just interact less with these depressions and hence exit first, and the small proteins stay behind stay behind, and will exit at the next step. Yeah.
How do I make sure that proteins don't stay inside the column?
So if you have some protein inside the column, you can change the pH, you can add a salt to compete these molecules on these depressions, or add some artificial substance, small one, again to compete with the small proteins on these depressions, and thereby pushing them out. You have ways to push them out, wash them out. Okay, so again, if it's counterintuitive, just remember the principle that the proteins that interact with the matrix inside the column are the proteins that will be delayed and that will hence exit last.
What does the chromatography mean?
Chromatography, the term comes from, if you really want to know, it's that historically, there's some historical reason. The German color industry, back in the 30s, 1930s or something, is what pushed these methods and made them more usable, and they have something with colors there, and hence the chromatography. Okay, I'm not sure what exactly the colors there, which part did they play there, but there is some separation of colors.
There's nothing with the...
No, there's nothing really with color today. Just the fact that we use these columns, still. So these methods are generally called chromatography. No, it has nothing to do with color anymore. And ion exchange chromatography separates proteins by their charge. And in this case, what you will find inside the columns are usually beads, but this time charged beads, and in this case positively charged beads. So if they are positive, the positive proteins that inside the proteins mixture that you enter the column will exit first, because they would not interact. If at all, they will be pushed out because of these beads and will exit first, and the negative proteins will stay behind, stick to the positive bead. And now, in order to wash these away, as you asked, you can change, what we call to elute them out. You can add a different concentration of salt, because doing so, for instance, the chloride from salt will compete with the proteins on the electrostatic interaction with the bead. And the negative proteins will be washed out as well. So you get separation, or at least a very fine enrichment, because you still have some salt. You can produce a very neat separation using ion exchange chromatography. Separated by a charge of the protein. Okay, the third and last example of chromatography is affinity chromatography. The beads this time are coated with an antigen that the protein to be separated recognize. So the proteins that recognize this antigen stay behind, while proteins that do not recognize this antigen have exit first. By the way, when you put the mixture into the column. And now, in order to elute these proteins that have recognized the antigen, you can change the pH by adding a different pH buffer, and you can do add some artificial molecule that will compete with this protein on the interactions of the antigen and so on.
You would choose your method based on what you already know about the protein. It's like you're separating for unknown proteins.
That's a tough thing too. If you're not sure which method would separate best a desired protein, then you would most usually use all of them, or at least as much as you can do in a single PhD time period. Usually we start by knowing something about something, and we start there, and then find out something new, and then continue with this new piece of information. You have to know something about it. Yeah, I agree. Okay, so these were the methods of separation using columns, what we call liquid chromatography. In addition, we have some specific enzyme and antibody assays that can detect individual proteins And here, we usually detect proteins not directly by measuring how many proteins do we have, but for instance, we can measure if we're looking for the how much enzyme do we have in the test tube. For instance, we can measure the loss of its substrate or the formation of its product. And if by definition we will start with two systems, two biological samples with the same amount of substrate or product, so a greater loss of substrate in sample A will denote that we have more of the enzyme in this sample, right? So we not necessarily always measure directly the level of an enzyme, but rather can measure something indirect, such as the loss of a substrate or the production of the product. Some enzymes utilize homogenic substrates, which are just very easy to measure. You can, if you have more light intensity inside a test tube, you have many machines in the lab to measure this intensity. And if your substance is for some reason not homogenic, you can add, and this is what certain kits or certain companies do, you add artificially some homogenic substance just to make the read more accessible and easy. Okay, Western blot is, I think, the most common way in labs to detect proteins, and it continues electrophoresis. So it begins with electrophoresis, separation by size, and if now you want to detect a specific kind of protein in this gel, you first need to transfer it to a membrane, cellulose membrane. This step is called transfer. And now we usually stain it with the first antibody, the primary antibody, that recognizes the protein under investigation. Then add the second antibody, secondary antibody, that recognizes the first antibody. So in the bands where the protein is absent, the first antibody did not attach, and that's why you will not find the secondary antibody there as well. Now, most usually the secondary antibody has an enzyme linked to its edge, which will produce some homogenic substrate upon addition of some molecule into this system.